These are the Chapter 9 Notes 1 on sampling distributions. Today we're going to talk about what sampling distributions are. We're also going to talk about what parameters and statistics are. We're going to look at what makes data unbiased, and we'll also talk about the variability of data. Now, before we get into that, I want to talk a little bit about this pennies activity. You're going to be working with the person sitting next to you, and this container of pennies is going to slowly make its way around class today. You're going to need to work relatively quickly. You can't take more than 5 minutes per group, so make sure that everybody in class gets a chance to do this. The 4 steps are holding the container tight. You're going to shake up the container of pennies to mix them up. Please make sure that you have the hold on the top of the container so that the pennies don't fall out. You don't want to be the person in class that's cleaning up 1,000 pennies today. Second step, you're going to count out 20 pennies from the container as randomly as possible, so don't just pick them up from the top layer. Work quickly, however. You're going to record how many of these pennies were minted after the year 2000. So if there were 6 of them, you're going to write a little 6 on your little worksheet here. You're going to divide this number by 20 to get the proportion of pennies in your sample that was minted after 2000. You're going to write that number in the little space provided inside the box. Then in step 3, you're going to count out an additional 30 pennies, so you have a total of 50. You're going to record how many of these pennies were minted after the year 2000. So if I get 10 more pennies out of this next 30 that were minted after 2000, that would give me a total of 16, or 16 out of 50, which would be 32%. This proportion I'm going to write in this little box right here. You're going to then pass the container to the next group of people so that they can get started immediately. And on the histograms on the board, you're going to put a box on the appropriate locations on the histogram corresponding with the boxed answer for number 2 and the boxed answer for number 3. So your answer for number 2 is going to go on the top graph, and your answer for number 3 is going to go on the bottom graph. So on to our notes for today. We're going to first off with a couple of definitions. One's for parameter and one's for statistic. The word parameter, you may have heard in other contexts before. Parameter starts with a P, and the definition is going to involve another P word as well. A parameter is a number that describes the population. And we use parameters a lot in math. You probably have used an abbreviation for a parameter for means before. The population for the mean is abbreviated with a Greek letter mu. This refers to the population mean, the mean of the entire population. For proportions, we use the abbreviation lowercase p to stand for a proportion. So if we're talking about the proportion of all pennies that were minted after the year 2000, we'd use p if we're talking about all pennies. For standard deviation, we use this notation, sigma. So we've got a Greek letter that we use for an abbreviation for a population mean, and a Greek letter that we use for a standard deviation of a population. Now statistics, this class is called AP Statistics, so we work with statistics a lot. A statistic is a number that describes the sample. And we have used some statistics in this class already. Now you may recall that we've used mu for mean. There's another abbreviation that we've used for means as well. When you go to 1var stats on your calculator, that's the abbreviation X bar, which officially refers to a mean of a sample. If we're taking a proportion from a sample, then we're going to use an abbreviation that says P, remember this thing, P hat. That's going to be our abbreviation for a proportion for a sample. And for standard deviation, we use our lowercase English s to denote a standard deviation taken from a sample. So some of these abbreviations you're familiar with, some of these are new, but from now on, there's a specific time and place that we use each of these abbreviations. So using appropriate notation, we're going to write these English sentences as math equations based on the abbreviations we've talked about here. If it says 80% of all Williamston High School students brought a smartphone to school, because we're dealing with everybody from Williamston High School, the key word is all. This is a population value. So using our parameters, this is a percentage or a proportion that's dealing with a population value. So we're going to call this P equals 0.80. P stands for proportion. Some people think of it as being like a percentage. Sometimes it could be thought of as a probability. They're all kind of synonymous with each other. These all go with parameters. It's all students, so it's a parameter, and we're dealing with a percentage. The standard deviation from a sample of 15 quizzes during 4th hour was 5.1. Because it's from a sample, we're dealing with a statistic here. It's a standard deviation, so we'll use the abbreviation S equals 5.1. See if you can figure out what the appropriate notation is for this last sentence. We'll pause the video real quickly and see what you come up with for that one. So usually if you're taking a mean, you're dealing with all the values. You're adding all the values, dividing by how many there are. So since we're working with all of the values, that would describe the entire population. This is a parameter. We'll use the abbreviation for parameter, or the population mean, which is mu, equals 1,930,500. So there we go. Now the graphs that we're going to be working on the board off to the side here, the yellow graphs, are examples of graphs that would eventually become sampling distributions. Now a distribution is essentially a list of data, and it's usually data that's been graphed. I usually think of another word for distribution is the word graph. So the definition I'm going to use here is going to include that vocabulary here. What a sampling distribution is it is a distribution or graph of values of all possible samples of the same size from the population. What this means is that we're going to look at a graph of all samples of size 20. We're going to look at graphs of all samples from size 50. And these graphs, these histograms, are called sampling distributions. It's graphs of samples. We're graphing everybody's sample in class. So each person that puts their 20 penny proportion up on the graph, you're going to create what's called a sampling distribution. This graph would eventually be a sampling distribution if we could take every single possible combination of 20 pennies, take that proportion and graph it. So if I had everybody from this class, my other AP Stats class, everybody in school, everybody in Ingham County picked out 20 pennies, and it was every single possible combination of the pennies that was out there, that would be what would be called a sampling distribution. Let's talk about a couple more definitions as well. We'll start with unbiased. Unbiased data occurs when the mean of the sampling distribution equals the true parameter being estimated. If we look at the graphs on the right side, the idea behind this is that your sample is, well, I'm going to say, on target. You're going to notice that there are a couple of graphs here that have low bias and a couple of graphs that have high bias. The ideal is to have low bias or no bias at all. What that means in this case is that pretty much your sample is on target with what the true average is. And you can see with these bullseye examples here, on the graphs on the right-hand side, you'll notice that the dots there are pretty much right in the center. So our sample is pretty much right on average, where we would expect it to be. If we have high bias, that means that the average of our sample points doesn't happen to be right on target. So what we want is we want unbiased data. We talked about this at the beginning of the year. We want our data to be free of bias, makes it more accurate. Variability. Another word for variability is spread. And the idea I want to bring up here is, with variability, as your sample size increases, variability decreases. Similar to when we talked about the law of large numbers, as we get a bigger and bigger sample size, as we increase, as we do more replication, what we should notice is that our data should be more on point. Sometimes if you do just a few samples, if you have a small sample size, we may get more variability in our answers. So if I say, hey, we're going to flip a coin 5 times, what percent of the time did you get heads? Could happen 100% of the time. Now, if we're flipping 500 coins, it's very unlikely, almost impossible for you to get 100% heads or tails. So you notice that as our sample size gets bigger, our variability decreases. We have more predictability. So a few statements here that we're going to answer as being more accurate, less accurate, or as accurate. In our first scenario, we're going to look at a sample of size 1,000 from a city of 600,000 residents, and we want to compare it versus a sample of size 1,000 from a city of 1,000,000 residents. Now, it seems like if you're taking 1,000 out of 600,000 compared to 1,000 out of 1,000,000, the first sample should be more accurate. What's interesting, though, is that both samples are equally accurate. Both samples have the same size. In statistics, if you're taking samples of the same size, they are as accurate from each other as possible. So it is not related to population. If you take a sample that's large enough, you're going to notice that a sample size of 1,000 from a city of 600,000 versus 1,000,000 versus 10 million, all those samples are equally accurate in describing the population. If we take a sample of size 1,000 from a size of 2 million residents compared to a sample of 500 from a city of 500,000 residents, what we're dealing with is we're dealing with a smaller percentage of people taken. If you take 1,000 out of 2 million compared to 500 out of 500,000, you're dealing with a smaller percentage of people here. However, sample size is key. The more people that are in your sample, the bigger the sample size, the more accurate your sample is. It's not based off of percentages of people. The variability of a sampling distribution is impacted by sample size. It is not impacted by population size. This is sort of counterintuitive, and we'll get into this more over the next few days as to why this is actually the case.